Welcome back. Let's continue doing problems. So we are in the middle of a problem session. In the last problem, we proved a very nice result about a Galois extension whose Galois group is S3 must be the splitting field of an irreducible cubic polynomial. Okay, let me continue now. That was fourth problem. So fifth problem is a simple statement which sometimes comes in handy. So let's take K and let's say there are two subfields L1 and L2, and let's say they are both going to contain F. So you have K and F and two intermediate fields, that is the point. So if L1 over F and L2 over F are Galois, then show that L1 intersection L2 over F is Galois. Okay, so let me just draw a bigger picture here. So you have L1, L2, then they both will contain L1 intersection L2. So if this is given to be Galois and this is given to be Galois, then we want to show this is Galois. Okay, so what I will not say anything about is the solution. I will assume that L1 intersection L2 is a field. Okay, so check this if you want, but it's very trivial because if A and B are both in L1 and L2, their product is there, their sum is there, and so on. So now we are going to again use the Galois equals normal plus separable, that characterization of Galoisness. So clearly L1 over F Galois implies L1 over F is separable. This implies L1 intersection L2 over F is separable. Because any sub extension of a separable extension is separable. So this is separable. In fact, you don't even need to know that L2 is separable. If L1 is separable over F, L1 intersection L2 is separable. So separability is clear. To prove normality, so suppose F is an irreducible polynomial and suppose F has a root in L1 intersection L2. Okay, so this I want to show that F splits completely in L1 intersection L2. That is one of the equivalent characterizations of normality. So F has a root, let's say alpha in L1 intersection L2. So F has a root in alpha is in L1 intersection L2. So it is in L1, so F splits completely in L1. Similarly, of course, F has a root in L2 also because the same root alpha is in the intersection. So it has a root in L2, so it splits completely in L2. Remember, the set of roots of F in some large splitting field is a fixed set. So that means F splits, those roots are same. Whatever are the roots of F in L1 must be same as roots of F in L2. So conclusion is F splits completely. All those roots are in L1 as well as in L2. So they are in L1 intersection L2. So the point here is the set of roots of F is a feature of F itself. It doesn't depend on an extension field because the set of roots in some splitting field is a fixed set. So you can always take a large splitting field of F which contains both L1 and L2. In that splitting field, the roots are a fixed set. So their F splits completely in L1 means that set is in L1. F splits completely in L2 means that set is in L2. So that's all. So F splits completely in L1 intersection L2. So L1 intersection L2 is over F is normal. So this implies L1 intersection L2 over F is Galois because we already argued that it is separable. Okay, so the only reason that I put a K here is to consider the intersection. So K is required here, otherwise K is not required in the proof. K is required here to talk about L1 intersection L2. See, intersection is a set theoretic operation. So to talk about intersection of two sets, they must sit inside some ambient set. So I need a K containing both L1 and L2. So that is why I took K. Okay, so this is a simple problem. So let's now look at the next problem, which asks the following. In each of the following extensions, find the Galois group and determine all the intermediate fields. I should also show actually, in fact, this is second statement. A is show each of them first show that each of them is Galois and then find the Galois group and determine the intermediate fields. So the first one, so let's do this. K equals Q zeta 8 over, so zeta 8 is a primitive 8th root of unity. So now I claim that first let's find the irreducible polynomial of this. So in order to find the irreducible polynomial, what we have to do is, let's start with some polynomial that it satisfies. So certainly it satisfies this, right? It satisfies this. So this factors like this. I claim that, let's call this fx. So claim f is irreducible. And this is simply a Eisenstein criterion statement. Of course, a priori it doesn't apply because the leading the coefficients are just 1, but change the variable to x plus 1. Then fx plus 1 will be x plus 1 power 4 plus 1, and then you see that it is x power 4 plus 4x cubed plus 6x square plus 4x plus 2. So then apply with prime number 2. 2 divides all the coefficients, 2 square does not divide the last coefficient. And also note that zeta 8 power 4 is not equal to 1 because it's a primitive 8th root. That means it is not a root of unity less than 8. If zeta 8 power 4 is equal to 1, zeta 8 is also a 4th root of unity, but a primitive 8th root of unity cannot be a 4th root of unity. So f of zeta 8 must be 0 because x power 8 minus 1 has zeta 8 as a root. Zeta 8 is not a root of this, so zeta 8 must be a root of this, and f is irreducible. So the irreducible polynomial of zeta 8 over q is x power 4 plus 1. Okay, so now that means k, which is q zeta 8 over q, is a degree 4 extension. The advantage of finding the irreducible polynomial is that we know the degree of this extension, so we conclude it is 4. Now we have to show that it is Galois, find its Galois group and find the intermediate fields. So now let's first show that it is Galois. So note that the primitive 8th roots of unity are, okay, so this is something that I mentioned before when we discussed this particular extension before many times. So the primitive, because zeta 8 can be taken to be cosine 2 pi by 8 plus I sine 2 pi by 8. So this is cosine pi by 4 plus I sine pi by 4. So in fact all the primitive 8th roots will be taken by, given by plus minus, by putting plus minus here, plus minus here. So this is just a parenthetical remark. So continuing here, are basically plus minus 1 over square root r plus minus I over square root r. So now I want to claim that k is actually equal to q adjoint I root 2. So the proof is, first I claim that I is in k. Why is this? I is in k because zeta 8 square over 4 is zeta power 8, which is 1. That means zeta 8 square is I or minus I. Depending on which primitive root we take, it will be either I or minus I. It doesn't matter which one. We conclude that zeta 8 is there, so zeta 8 square is there, or minus zeta 8 square is there. So I is there. Once I is there, we can use the fact that 1 over root 2 plus I over root 2 is in k, and we just concluded that I is in k. This implies, so also we know that 1 minus, okay, so actually, so we don't need I is in k, I guess. So this is in k because once a primitive 8th root is there, all its powers are there, and these are cyclic, so each of them is a power of the other. So these are there, that means their sum is there, which is 2 times 2 over root 2. So both I and root 2 are there. This means q adjoint I comma root 2 is contained in k. So let me write like this: k, which is q adjoint zeta 8, which is going to contain. So this is already 4 because, of course, this is 4 because I and root 2 you can consider. So this I'll write down once, but so this is 2, this is 2, but this is 4. So this must be 1. So this implies q adjoint I root 2 equals q adjoint zeta 8. Actually, we can conclude Galvanese in any number of ways, but one way to conclude that is k over q is Galois because one reason, k is the splitting field of x power 4 minus plus 1. Okay, so that shows that it is a splitting, it's normal, and we are in characteristic 0, so it is it is separable, so normality is all required. So, or we can alternatively argue that is normal because I minus I are the conjugates that are there, and root 2 and minus root 2 are conjugates are there, which are both there. So this is something maybe, I mean, this is a bit vague, but we did this earlier. So I am giving 2 alternate arguments. So this is Galois. So now that means, so the cardinality of the Galois group is equal to the degree of the field extension, which is 4. So this implies, now let us determine the, is either Z mod 4Z, there are only 2 groups up to isomorphism of order 4, or Galois group is not cyclic. So either it is cyclic, then it's Z mod 4Z, or it's Klein 4 group, in which case it is Z mod 2Z cross Z mod 2Z. But which one is this? And here is where we are going to use main theorem. If it is the cyclic group, then K over Q has exactly one intermediate field L such that K colon L is 2. Of course, in that case L colon Q will also be 2. Why is this? Why is this? This is because Z mod 4Z, so this is Z mod 4Z. Z mod 4Z has exactly one subgroup of order 2. So any intermediate field with degree 2 corresponds to a subgroup of order 2 of which there is exactly 1. Okay, but this is the point, but K over Q has more than one such intermediate field. Right, this is clear to us because it contains Q root 2 and Qi. So, okay, so this is something that I should at some point say, but these are not equal because this is in R, this is not in R. Okay, so these are distinct. So hence, see, this is the opposite direction. We know something about the field extension, we are concluding about the Galois group. Hence, Galois group can't be cyclic. It has to be isomorphic to, and then that determines the Galois group, right? So in each of these cases we have to show its Galois, which we did, find the Galois group, which we did. Now finally find the intermediate field. Now we will use the opposite direction of the main theorem, knowing something about groups to conclude something about intermediate fields. This group has 3 subgroups of order 2, which give you this, but there is one more, right, which of course is, so final picture is, it has 3 subgroups of order 2 and 2 more subgroups, the entire group and the trivial group. So the final picture of intermediate fields is Q root 2, Qi, what is the third one? If you think about it, that's just Q root, Q adjoint, I root 2. We discussed this at length. So there are 5 total subgroups of G and 5 total intermediate fields of K over A. Okay, so this is the picture. So that completely analyzes this problem. So this is 1. It is first part of 6. So let's do second part. Okay, so this K is the splitting field . Okay, so K is the splitting field of this polynomial. So this is automatically, hence the first step is trivial. So what we need to do is to find the Galois group and the intermediate fields. But what are the roots of this? So what are the roots of? So in order to find the roots, let's find out the factorization of this. In fact, this is not irreducible. Okay, so this you can factor as x square plus 2x minus plus 2 times x square minus 2x plus 2. Okay, this is a simple calculation. I can check that, you can check this. So this is x square plus 2x plus 2 times x square minus 2x plus 2 is exactly x power 4 plus 2. Now what are the roots of this? Roots of this by binomial quadratic formula are equal to 2 plus or minus b plus or minus b square minus 4ac, right? So 4 minus 8 by 2, and the roots of this are 2 plus or minus 4 minus 8 by 2, right? And this gives us 2 plus or minus square root of minus 4, so that's 2i by 2, and this gives 2 plus, so this is minus 2 plus or minus that, this is 2 plus or minus 2i by 2, because square root of minus 4 is square root of 4 times square root minus 1, so this is 2i. Okay, so this gives us the set 1, so minus 1 plus minus I and 1 plus minus I. So the roots of x square plus x power 4 are, there are 4 of them. So this 1 plus I, 1 minus I, minus 1 plus I, minus 1 minus I. So these are all going to be in K, and K will be generated by this. So they are all in K, but then I is in K because 1 plus I is in K. So 1 plus I minus 1 is in K. So I is in K. So hence K is Qi. I mean, this kind of argument we have done several times. So K over Q, Qi, Q. So now each of these roots, let's call them alpha 1, alpha 2, alpha 3, alpha 4. They are all here. Right. So once I is there, 1 plus I is there, 1 minus I is there, and so on. So they are all there. K is generated by them. So K is equal to Qi. And hence the degree extension of the extension is 2. This shows that the Galois group is, there is only one group of order 2 up to isomorphism. So that is it. And the only intermediate fields are K and Q. So simple enough. So K is Qi, Q, and no, nothing here, nothing properly here. So there are only 2 intermediate fields. Okay, though it's a degree 4 polynomial, remember splitting field can have degree smaller than 4. It can be at most 4 factorial, but it can be smaller than 4. Okay, so that's 2. So let's do one more. Let's see x cubed splitting field of x cubed minus 2 over, let's do f2, f3, f4, sorry, f5, f7. Okay, so I think I have written these 4 things. So I'm going to take 4 fields and look at all of them. So first, x cubed minus 2 over f2. So x cubed minus 2 of course is x cubed, and splitting field here is f2 itself, because the only roots are 0. So this is trivial, and the Galois group is identity, and there is no intermediate field. So x cubed minus 2 over f3. Okay, what is this? So this, so this I claim is what are the roots of this? So degree 3 polynomial, so I can quickly check the roots. So f3 has 0, 1, 2, right? 0 cubed is 0, so 0 is not a root. 0 is not 2, right? So any root must have cubed is equal to 2. 0 is not a root. 1 cubed is 1, which is not 2. So 1 is not a root. 2 cubed is 2, right? So this implies 2 is a root. So in fact, x cubed minus 2 is x minus 2 whole cubed over f3, right? So it is not a separable polynomial because the derivative is 0, so not separable. Okay, actually not that, I can't say not separable, but it has repeated roots because it's not irreducible, so I don't want to talk about separability. So it's x minus 2 whole cubed. So what is the splitting field of? There is only one root 2 and it's already in f3, so it is f3 itself. So just like in the case of f2, k is f3, and G is identity. Okay, so Galois group is identity. There is nothing to do here. Not finally, but f5. So in this case, I claim that 2, or rather minus 2 is a root. So let's say, what is 0 cubed? So let me just check the roots. So 0 cubed, so you can check all of them, but 2 cubed is, or 3 cubed, let's say 3 cubed is 27. So implies 3 cubed minus 2 is 25, which is 0 in F5. So 3 is a root of x cubed minus 2. So we can write, so I have already done this calculation, so I am going to go over this fast, but it is x minus 3 times x square minus 2x plus or minus 1. Okay. So this is something that you can check. This is simple calculation. So check this. So it is not irreducible, it has one root, but you can also check that this is irreducible. Because it's a degree 2 polynomial, all you need to check that is that it has no roots. Check that x square minus x plus 1 has no roots in F5. For example, if you take 1 square, 1 minus 2 plus 1 is, sorry, this is minus 1, I should have written. So what you get is minus 3 minus 1, so that's plus 3, which is minus 2. Okay. So this is minus 1. If you do 1 minus 2 minus 1, that is 0. That is not 0. So check that there are no roots. So the conclusion is K, which is the splitting field of x cubed minus 1 over F5, is actually the splitting field of x square minus 2x minus 1 over F5, and x square minus 2x minus 1 is irreducible. So hence K colon F5 is 2. Okay. So K is a degree 2 extension of F5. It is the irreducible, it is a splitting field of an irreducible degree 2 polynomial. So it must be degree 2. So it just happens that Galois group, again there is not much choice here, is Z mod 2Z, and there are no non-trivial intermediate fields, right, because it's degree 2. So any intermediate field is either K or F5. So there are no non-trivial intermediate fields. And finally, let's do F7. F7, it just happens that this is something I'll check. I'll ask you to check that x cube minus 2 is irreducible over F7. Simply check that x cubed minus 7 has no, or minus 2 has no roots in F7. Because it's a degree 2 polynomial, if it fails to be irreducible, it must admit a root in that field. But you can check, there are only 7 elements, 1 cubed is not 2, 2 cubed is not 2, 3 cubed is not 2, and so on. So you can check that it has no roots. So K over F7 is the splitting field of x cubed minus 2. So I need to do some work here. So it is the splitting field of x cubed minus 2. So the question is the Galois group. Okay, so K colon F7 is either so K colon F7 is either 3 or 6. Okay, so I haven't worked this out in detail, but in general, if you have a irreducible cubic polynomial, its degree is its degree of its splitting field is either 3 or 6. Okay, so either by attaching one root you get all the other roots, or you don't get all the other roots. Okay, so basically what I am saying is that let alpha be a root of x cube minus 2 in F7. Okay, so what we have is, so then we have k, f alpha and f, which is of course F7. So there are two possibilities. Either f alpha equals k, in which case k colon f will be 3, and Galois group in this case has to be Z mod 3Z. It's a degree 3 extension. In other words, it's a degree 3 order 3 group. This is one possibility. Or f alpha is not equal to k, in which case this will be a degree 2 extension and this will be a degree 3 extension. This is of course 3 because irreducible polynomial is degree 3. So in this case k colon f will be degree 6, and what we know for sure is that because of the first problem that we did in this problem session in the previous video, the Galois group must be cyclic. So this must be Z mod 6Z. So in which case there will be some intermediate fields, in which case, in this case, there are no intermediate fields. So I am running out of time, so let me stop this video here. In the next video I will argue that in fact this occurs. So we will show that k equals f alpha. So it is in fact this case occurs and this case doesn't occur. Okay, so we will show that that is the case, and then we complete this problem, and then in the next video I will start with this, and after finishing it I will do some more problems. Thank you.